We left off in the last video talking about the error, and what I want to talk about in this video are two things. The first is what's called decomposition, and then we're going to go back into some forecasting. So with decomposition, we may want to model different features of a time series, and the goal is to better understand the time series. So I might like to understand a little bit more about the seasonality of the time series as well as the trend cycle component. And the thought process is that there's a lot of variation in the future value of a random variable over time. And some of that variation is random and some of it is not. And it may be difficult for me to perceive that variation just based on looking at the raw data or looking at a graph, or I may not even identify there as being, I may not be able to distinguish the variation from being systematic from being random. And so you kind of run into these circumstances where understanding the data, getting an idea of, okay, well, what does the data look like if we remove the seasonality? What does it look like if we remove the trend? How strong is the seasonality? And just maybe to get a good idea of where this could be a problem. Let's have a look at some of our previous graphs. Here's Amazon revenue. It is clearly trending up over time. It clearly has a large seasonal component. So how big is the seasonal component? That matters. If you're Amazon, you definitely want to know the magnitude of the seasonal component. But if you're planning on the growth of the business, you want to know the magnitude of the trend component. So I want to know both. I see the time series going up substantially over time, but short-term planning requires pretty accurate forecasting of the seasonality, and long-term planning requires me to think about the trend. Take a look at consumer debt service payments as a percent of disposable personal income. So I see this trend component to it, and I want to know whether or not I'm leveraged as a consumer. I can look at this percent of consumer debt service payments as a percent of disposable personal income, and that also gives us some insight as to like what spending will look like in the future. Look at Georgia construction, Georgia manufacturing GDP. Clearly, decomposing some seasonality out of this might be important, particularly for the manufacturing. So we see these different time series features, and we may want to deconstruct the time series. And here's a nice example of it. Here's personal consumption expenditures, and this is just real spending in the economy. And so you can see that spending is quarterly. All right, so as time elapses, people have been spending more over time in real dollars. Okay, however, it's seasonal. And so you can see that every 4 quarters we see some seasonality, and we would like to know how much spending is trending up over time, but we might also like to know a little bit about how it changes during the season. So this is the data, and I just pull it from 2016 to 2020, and you can see that real personal consumption and expenditure per person per quarter has been trending up over time. But then if you take a look at COVID-19, basically personal consumption expenditures fell back to the level that they were prior to Donald Trump being elected. So consumption spending had gone up appreciably over this time period, and then COVID-19 knocked it back down to kind of where we were in the Obama-Trump transition period. Okay, so this is time series with clear trend. It's time series with clear seasonality. And what we would like to do is estimate the trend first. So when we think of a decomposition, I'm taking apart the time series. I'm decomposing it into a seasonal component, a trend component, and a remainder. So Y is the time series. S is the seasonality. T is the trend. R is the remainder. So when we talk about a seasonally adjusted time series, we're taking Y and we're subtracting out the S. when we think of a time series that has Y removing both the seasonality and the trend, that remainder should look a lot like white noise. So it should look a lot like this. We don't want to see there to, we would like to see there be a small amount of random variation afterwards. And so this is what we call a classical additive decomposition. Now, we could do a classical multiplicative decomposition where instead of netting out the seasonality and the trend by subtracting and adding, we could divide it out. But we're going to do the additive trend. This is the easiest one to do. So in order to net out the seasonality, the trend, to get a remainder, you actually have to estimate the seasonality and the trend, and so we're going to do that right here. So we're going to estimate the trend with what's called a K-period moving average. This is not the average method of forecasting that we talked about earlier. So we're not doing this. Okay, this we look back in the past, and we make a forecast. Here we are using both data in the current period and the future period. So K-period moving average is going to incorporate the current period, some data from the past, and some data from the future. K is the number of periods included in the moving average. So if K is an even number, i.e. 2, 4, 6, 8, we're going to include one more period from the past than from the future. So it's asymmetric around the current data point. So if you have a 4-period moving average, then it's calculated by taking 2 periods from the past, the current period, and 1 period from the future. But that means you're taking more from the past than from the future. So if K is odd, the forecast is symmetric. So if we have, say, a 7-period moving average, then we have 3 data points from the past, 3 data points from the future, and the current period for a total of 7. If K is monthly, if it's 12, then we have 6 periods from the past, the current period, and 5 periods from the future. This is not necessarily a problem. So if we have an even number of periods in our moving average, we can average the forecast afterwards. So, let's say I have 4 periods, 7 periods of data. All right, I start making a 4-period moving average in period 3, and that includes periods 1, 2, 3, and 4. Then in period 4, I include periods 2, 3, 4, and 5. Okay, if I just average together those two moving averages, they both share periods 2, 3, and 4, and I can make an estimate that is symmetric by just averaging those together. So let me give you an example with this personal consumption expenditure data. So the 4-period moving average, I can't make one for period 1 and period 2 because I don't have periods in the past to do it with. But for period 3, I take quarters 1 and 2, quarter 3 and quarter 4. I average them together, just add them up, get this average. I can't do a 2x4 moving average, but if I do a 4-period moving average for quarter 4, so I take quarter 2, quarter 3, quarter 4, and quarter 1 of the next year, if I average these together, I'd have another 4-period moving average. Then if I average together those two averages, okay, I will get, and this should be 3883.10, I will get a 2x4 moving average, but that 2x4 moving average will have just one observation of quarter 1 of 2016 and quarter 1 of 2017, and 3 each of quarter 2, quarter 3, and quarter 4. So it will be centered on quarter 3. And so if I go back through here and produce a 2x4 moving average, I actually have a symmetric forecast. Okay, and I could move those up a period. So we detrend the data. How do we detrend the data? We remove the moving average. Okay, we remove the moving average. So I take the data, I subtract out the moving average, and then I have something that's seasonal with the remainder. So if we go back to the decomposition strategy, y is equal to s plus t plus r, I estimated t in two different ways. Here's an asymmetric moving average, here's a symmetric moving average, and here is my detrended data set. Okay, y minus t. So next I average together the seasonal components to get S. And so I can just take an average of each season for the seasonal component. Now, there is some debate over whether or not you need these to average to zero, but this is not necessary as long as the remainders are mean zero, I don't think. So, do the seasonal averages need to average to zero? I don't think so, as long as the remainders are mean zero. So here's the detrended time series where I take the data and I subtract the moving average here. And then I have that detrended. I subtract out the seasonal component, which is consistent, and I get a remainder. This average is mean zero. So R will decompose a time series for you, and it has a decompose function that will produce this decomposition for you. So what is it that we're trying to do within R? We are taking a time series and breaking it into three different parts. One represents the seasonality. So every year in quarter four, people spend more. How much more? Well, we figure that out by first stripping out this upward slope. We strip it out, so all we have left is the variation. Up, down, up, down, up, down. Then we estimate the up by averaging the ups. We estimate the down by averaging the downs. And those averages are our estimates for S. The slope of the time series is estimated by the moving average, and that's either a KMA or a 2 by KMA. Our time series can now be deconstructed into Y minus T. That's where we remove the moving average. Then we subtract the season, and what we have left is the remainder. That remainder should look a lot like white noise, okay? Average of zero, roughly. And you can see there's nothing especially systematic in the misses. Now, STL decomposition is something that R will produce. It's very difficult to do by hand, but it's a variation of decomposition that's nonlinear. R does it for us automatically. So we just run model STL, take the time series that you want, and here I've decomposed some unemployment data from Miami-Dade County. This is the time series. Smooth out to, here's the trend. Here's the seasonality, and you can see it kind of opening up a little bit more, and then here is the remainder, and you can see the remainder is essentially mean zero. Now, occasionally we'll want to produce what's called a seasonally adjusted data set. So this is something that you may be asked to produce for your organization, particularly if you're dealing with some type of retail sales measure where customers buy things in different ways at different times of the year. Well, what do we do then? How do we construct a seasonally adjusted data set? We call it AT, seasonally adjusted data at time T. I'm going to take the trend, I'm going to add the remainder. Okay, and what we have here is a data set that no longer has any seasonality in it whatsoever. So you can take a look at this, take the trend, you add in these remainders, and you're actually going to see a very, very smooth increase over time in personal consumption that doesn't have any of this jaggedness in it. So there's no jaggedness, it's just a smooth increase up to this point. You can take a look at this column here. You see just a smooth increase in consumption over time, despite the fact that the actual data, it looks like this. So that is a seasonally adjusted data set. And of course, left unsaid is the fact that in this table here, I excluded COVID entirely. Okay, and so you don't see this precipitous decline in personal consumption expenditure. And I think it's worth noting, as far as looking at the response of consumers to the pandemic, that we are still not anywhere near recovered to previous consumption levels. So if you look at quarter three of 2020, it's lower than quarter three of 2019 and quarter three of 2018, and it's in the vicinity of quarter four of 2017. So we have seen a huge decline in consumption expenditure. Consumers start spending as much as they did prior to COVID-19 in any way. We've lost almost all of the consumption spending that we had over the last 4 years. All right. So the seasonally adjusted data set is what is commonly produced on sites like Fred, BLS, etc. When you download this data set, it's important to note that a decomposition was performed. So somebody decomposed the data set for you when they produced a graph associated with seasonally adjusted data. They did a decomposition. It may have been an STL decomposition, which is nonlinear. It may have been a classical decomposition, which is what I show you how to do here. It could have been additive. It could have been multiplicative. But the idea is they produced a for you by estimating the trend, either with a moving average or something else. Okay, so when we think of this decomposition, you could actually conceptualize just decomposing the data set and then forecasting the decomposition component. So rather than trying to forecast Y, it may be beneficial for us to think about forecasting T or forecasting S. So if we do a naive model with trend, we could forecast the T. We could also do a double exponential smoothing model, which I'm going to talk about here in a minute, or we could do an ARIMA model. The seasonal component could also be forecasted with something like the seasonal naive model. This is not going to account for trends, so we may want to use a triple exponential smoothing. But the point of this is that we could take a stab at trying not just to forecast the data, but we could also forecast the trend, and we could also forecast the seasonality. And just to give you kind of like an idea of why forecasting the trend and seasonality may be a more desirable strategy is take a look at the 2x4 moving average. It is going up by about 22, 23, every period. It would be pretty doable to make a forecast for T, okay, and then it would be also doable to make a forecast for the detrended data. And then if you just tack on a mean zero remainder, you might actually have a pretty good forecast, whereas it may be challenging for you to pick up on the pattern of the trend and the seasonality in the data together, but forecasting the decomposed parts might actually be a pretty smooth process. So when we think about forecasting the decomposed elements like the T and the S, and assuming that the remainder is mean zero, might actually be easier than forecasting the time series itself. So if you can strip out a very consistent trend from the time series, it may be worthwhile to do so. And the good news is that it's pretty easy to do with either a KMA or a 2x-KMA. So the MA itself is not a forecasting method, but I could apply a forecasting method to the moving average data that I construct here to potentially make a good forecast into the future. And I think it's also worth considering that if you look at the MA, it incorporates future data into the current MA. So you might even be able to extrapolate past where you use the data for the MA and still make a quality forecast for a few periods out. Okay, so when we think of decomposition, it is a mechanism for us to understand the time series, but it is also potentially a platform for us to make a forecast that does not involve the data itself directly, but rather components of the data. So it may be easier to forecast these components than the data itself. So let's take a look at transformations. Transformation is different from a decomposition. So with a decomposition, I'm extracting different parts of the time series, but a transformation is just taking the time series and applying a function to it. And so I'm going to take the time series, I'm going to map it to the real line. And the thought is that maybe it's easier to examine the time series on a different part of the line than it's currently at. So some common transformations that we're all familiar with, think of inflation adjustment, think of population adjustment. I mean, we don't think of the income in Carroll County as being the sum of every person in the county. We think of it in a per capita way. We don't think of people's income in terms of just the amount of money they make. We divide it by the price level. So, you know, if I earn $70,000, that's nice. I need to think of what it can buy. That's really what matters. Okay, and so these are some common transformations that we're very familiar with, but I want to just point out some transformations that we may be unfamiliar with, and one's what's called a Box-Cox transformation. And so W is our transformed time series, and I take the natural log of the time series. So we're doing something very similar to what we did with regression in that we're taking away the interpretation from being at the unit level to a percent level. And otherwise, I can apply a power function where I raise y to the power of lambda, subtract 1, and divide by lambda. So think of it as like a constant elasticity or something like that. And this is used when the variation of the time series increases or decreases as the time series elapses. So as the time series goes further into the future, variation gets a lot larger. And a good example of this, if you take a look at the Dow Jones Industrial Index, let's look back over the last 5 years. Look at the amount of volatility here versus the amount of daily volatility here. You can see that this time series actually has an increase or decrease that has gone up over time. So the stock market has become more volatile in the last, say, 3 or 4 years. It's gone up, it's trending up, but you can also see these ups and downs have increased a lot relative to the past. Okay, so let me just show you a sample Box-Cox transformation. We'll take two different views. One is if lambda is equal to 0, we'll just take the natural log, and here's the per capita, the personal consumption expenditure again. You can see I just took a natural log of the data, and you can see I shoved it down from ranging from 3,000 to 3,440 to 7.99 to 8.14. And so this essentially just flattened it out. And then you can look at lambda equal to 0.25, and we're shoving it into a space from 25.5 to, say, 26.63. So the Box-Cox transformation, what you want to have happen is for the volatility to look the same across time periods. And so we want the size of the gap to not be as large with this transformation. Now, this smooths out the range of the data. It does eliminate large seasonal variation, but it also, and I guess you could think of this as kind of being in the same ballpark as with a regression where you're adjusting your standard errors to deal with heteroscedasticity. Here, we're adjusting the data before we ever get started with forecasting to account for the fact that there's increased volatility as time elapses. And okay, so we've done the Box-Cox, and we could make a forecast of, instead of forecasting PCE, we could forecast the Box-Cox transformation using any method we want. Okay? And then what you do is you just reconstitute the data as the original data set. So, you know, if I took a natural log, I raise it to the e to the w. Otherwise, I solve for y. So it's very doable to just reconstitute the time series into the original data series. And that may be something that we want to do. Okay, so we've talked about decomposing and transforming the data as methods of understanding the data more, or maybe transforming the data into something with properties that we like better. We haven't actually done any forecasting. So I'm going to introduce two new models today. One's what's called the exponential smoothing model, and the other is what's called the double exponential smoothing model. And then we will spend time talking about the triple exponential smoothing model. So all of the previous forecasting techniques, and we haven't covered too many, but the previous forecasting techniques that we've covered in this class have been the naive model, where the data for today is the data from the immediate past, and the average model, where the data for today is an average of previous time periods. These are baseline models easily implemented. They both have a limitation in that they do not use all of the available previous data. So I have a bunch of data here in this PCE data. The naive model would use exactly one data point. The average model, you can pick how many you want in the average, but once you observe another period, if you apply the same method, you forget the last period that you used. Yeah, both of those methods may be a little bit less than desirable. So I may not want to forget data. I may want to use the data, especially if I've bothered to transform the data so the data are all kind of in the same space. Why would I want to forget the data? Why would I want to, why would I bother to do a transformation and then just immediately use the most recent past? Why wouldn't I take an average of a large number of those Box-Cox lambda equals 0 or Box-Cox lambda equal to 0.25? I've bothered to transform the data into the same space. Why then wouldn't I use that data to make a forecast? And so I do want to use the data to make a forecast, and I can do that with the exponential smoothing model. And so this is kind of an intermediate forecasting technique. It does account for all previous periods, but there's still a predefined way for how the data are used. So this is the single exponential smoothing model. It is not suitable for any trend in the data, so this model is not going to do well in this situation here, where we're trying to forecast the 2x4 MA. Won't be successful. That's okay. Alpha is between 0 and 1. It's the percent of the forecast dedicated to the immediate previous period. So how much of this do we want to look like the naive model? That's a selection we can make, although we have some reasons for why we pick certain alphas, and we're going to try to pick an alpha that just minimizes the amount of forecast error. But if alpha is close to 1, then the forecast is essentially similar to the naive model. So how it works: alpha times the previous data, 1 minus alpha times the previous forecast, and the previous forecast is included in our model. So we have all the previous periods included because the previous forecast is included. Let's take a look as to why. How did we make the forecast for period t minus 1? I just took everything back a period. I moved one period to the left on the timeline. I got alpha times the data from 2 periods ago plus 1 minus alpha times the forecast for 2 periods ago. And that's how I constructed yt minus 1 hat. Aha, but yt minus 1 hat is in yt hat. So I can substitute this portion right here into yt minus 1 hat. Well, the cool thing about this is what made the forecast for period t minus 1? Well, data from period t minus 2. So even though you don't see it necessarily, it's included in the last term. So my forecast for period t, I have alpha times yt minus 1 plus 1 minus alpha times alpha yt minus 2 plus 1 minus alpha yt minus 2 hat. And you might suspect that we made yt minus 2 hat in the same way that we made yt minus 1 hat. We used data from yt minus 3. So all of the previous data are included. They're downweighed in a pre-specified way. So if alpha is equal to 0.7, then 70% of the forecast comes from period t minus 1. 30% of the forecast is everything else. Of that 30%, 0.3 times 0.7, 21% of the aggregate forecast is from t minus 2. So 70% from t minus 1, 0.3 times 0.7, 21% from t minus 2, 0.3 squared, and that's the exponential part. 0.3 squared is 0.09, 9% is the rest of the data. So with the average method, we think of chopping the data from the past into equal slices, but with the exponential smoothing, not so. Not so. What we do is we weigh the previous data according to alpha. Okay, so let's take a look at how it works, and I actually go back to the slides real quick here. Let's open them up because we can't see the alpha equal to 0.9. So let me just go back to the slides here. We'll make it a little bit smaller so we can actually see that. And we'll reopen it in Adobe. All right, there we go. So let's reopen it here. All right, there we go. Perfect. Let's take a look at alpha equal to 0.8 and alpha equal to 0.9. And I just want to show you how the data are included. So the naive forecast is the first forecast for everything. Then 0.8, YT hat. I'm making a forecast for October the 12th. This is the closing price. So what I did here is I just took this data related to Southern Company share price, and I went back through and I'm applying an exponential smoothing forecast to it instead of the naive and the average. So here's the baseline naive. Here's what the smoothing looks like. I take 0.8 times the previous data plus 1 minus 0.8 times the previous forecast. The previous forecast is localized to the alpha equal 0.8 column. Okay, and so with the exponential smoothing model, alpha is going to dictate how much of the forecast is associated with the previous period. So when alpha is equal to 0.8, 80% of the forecast is going to be the data from the previous period. And so I should expect my forecast to be awfully close to the previous data. So take a look at, the 19th. 58.04 is the data. I should expect the forecast to be pretty close to 58.04 relative to the previous forecast. I take 0.8 times 58.404. That 80% is there. The old forecast was 58.2867. But you can see that this forecast is not equidistant between the old forecast and the old data. It's much closer to the old data. And that is a hallmark feature of this forecast. Exponential smoothing 0.9 instead of 0.8, you can see it gets even closer to the old data. Even closer. So how we make an exponential smoothing forecast, we take alpha times the previous data point and 1 minus alpha times the previous forecast. Now, R automatically chooses alpha for us. And you might think that the goal would be to minimize the mean squared error. And if you were using a methodology like Excel, what you're going to do is minimize the mean squared error. However, you can actually use some nonlinear solving techniques to get even closer with your forecast. So there are two primary error criteria that are used within R. One's what's called a K-key information criteria. And what we do is we just try to get the AIC to be as small as possible. So this is the criterion. We have -2 times the log, this is what's called a log likelihood function plus 2k, where the likelihood is an estimated function that describes the probability of observing our data given a combination of parameters. So the parameter in this model is alpha. And we have an initial value. We use the naive, but R will actually pick something for us. So R might not choose 58.71, but if you're doing this by hand, you just pick the naive. And then R will also use the variance of the errors as your method of looking at the mean squared error. So R is going to pick alpha, pick the initial forecast, and pick the error variance to make this information criterion to be as small as it possibly can be. And the thought process is that the smaller this is, then the better quality forecast. The log likelihood, we want it to be as close to the data as we possibly can get. So think of the likelihood as we're choosing an alpha to get as close to the data as possible, and what measures how close to the data we are is the likelihood function. So this is done automatically in R. The Bayesian information criterion is also done, and it's just a transformation of the Akaike information criteria based on the number of data points that we use T, as well as the number of parameters. So it accounts for the amount of data that's included. You do not have to worry about this necessarily because R calculates the optimal alpha for you based on these criterion. However, it's not exactly using the mean squared error. So the Akaike information criterion, it does use the squared error. It's going to use the error variance, but it doesn't just seek to minimize the sum of squared errors. It also takes into account the number of parameters that you're using, and it does a nonlinear estimation. So think of R as taking a derivative with respect to alpha, the error variance, and the initial forecast. It takes 3 derivatives to a function where it doesn't know what the function looks like exactly, and it iterates to find a solution. And it does it quickly. So I think a good way of thinking about it, if you're thinking about it in terms of economics, is think of going to the store and you've got a utility function. It's kind of specified. It's kind of not specified. You know what's in your utility function, but you don't have a you don't have a sheet of paper which says, well, I get log apples plus log bananas plus this. You just pick a set of goods based on your budget that maximizes your utility. Well, R is picking an alpha and error variance and an initial state to minimize the Akaike information criterion, which is a description of how far away the data are from the forecast. Okay, so I don't want us to dwell too heavily on this. What I want us to do is just think that maybe we don't have to choose alpha. R will choose it for us. And so in our R demonstration, I will show you how to use R to make these exponential smoothing forecasts. But when you're doing it by hand, minimizing the mean squared error would be just fine. And you could do that in Excel with the solver. Okay, so let's talk about what the single exponential smoothing model is good at doing. It's good at making a forecast without trend. What is it not good at doing? Making a forecast with trend. Not so good. Not good at doing that. So let's take a look at forecasting with trend. If the data are trending, I would love to capture that. And so what we did earlier is we estimated the, we decomposed the time series. We knew it had trend, but the exponential smoothing method doesn't capture it. So we do what's called the Holt model. And so this is a forecasting technique. Note the T+1, different from a decomposition. So we go back to the decomposition. We're not forecasting anything. Not forecasting anything. This is YT. I have the data. I'm breaking it apart. With a double exponential smoothing function, I don't have the data. Don't have it. I'm making a forecast for what I think it will be, YT+1. I decompose it into 2 parts, a level and a trend. The level consists of the data, the old level and the old trend. The trend is a change in level and the old trend. So think of the level as being where the time series is right now. And the trend is where we think it's going. And so I make the forecast by adding, where's the time series right now? Where is it going? Alpha and gamma are both smoothing parameters. So alpha has the same meaning as it does previously. It's the percent of the level dedicated to the current data. Gamma is the percent of the trend that's based off the current data minus the old data. We can initialize this by creating a generic period and fitting a regression line. Let's just assume we do that in the interest of time. but I want to show you some data. So these are COVID cases in DeKalb County. Here is how we make the double exponential smoothing forecast. Take a look at the third, and I'm going to zoom in. I know it's difficult to see these slides. I'm going to zoom in a little bit more. Okay. All right, these are the cases. Okay, this is the current data. You can see the current data all the way down through here. These are the cases of COVID-19 going through Saturday. And this is the old level plus trend. We made a forecast by taking the level and the trend from the second and adding it together. So I forecast, and I used all the data to do this, I forecast 22,894 cases, and the total number of cases were 22,914. So how it works is I take that 22,914, okay, that's the new information I have. 80% of my idea of where the level is comes from the new data that I have. So this is what I forecast coming into the period. This is the new data. So 80% of where I think the time series is right now consists of the new data. 20% consists of where we were. How much do I think it's going up? Look at the new level that we just made. Take the old level that we used to make the forecast. Subtract. That's the difference. Think of it as like a stair step. And then 30% is the old trend. So I take that level, I take that trend, I add them together, I make a forecast. I look at the new data. 80% of the level comes from the new data. 20% comes from the old forecast. So you add them together, you get a new level. Then take the difference between the levels. Okay, take a difference between the levels here. And we get the old trend here. Okay. And I make a new trend. So difference in levels, old trend. How do I make the forecast? Take the level that we estimated, take the trend, add it together. I predict 23,359.40 going into the 5th. I predicted 23,359.40. It was actually 23,332. Comment about this is that we made a forecast that was way too low, but we immediately caught up with the next one. So I'm really weighing what I currently observed heavily here. Now, we just keep doing this, and you can see these are kind of one period ahead forecasts, but let's say I wanted to make a forecast for a couple weeks out. I have a couple of options. The first is just to multiply the trend by the number of periods out that you want to go. The second is to do what's called damping. So phi can be a parameter where it's between 0.8 to 0.98 typically, but think of this as a way of just imposing some structure on the forecast to make it a little bit more nonlinear. So I kind of turn it into a log function. And the idea here is that, let's say I want to forecast 10 periods into the future. Well, instead of just multiplying the trend by 10, I do 0.8 plus 0.8 squared plus 0.8 cubed all the way to 0.8 to the 10th times t. And that makes that prediction a little bit smaller. So if I were forecasting cases for Thanksgiving in DeKalb County, this is what a linear trend would look like. This is what a damped forecast would look like. And you can see the difference there. So it may be appropriate if we want to slow down the rate of growth for the future. Damp trend forecasting is actually a very, very prominent type of forecasting that's done routinely by businesses. So think of sales. Do we think we're going to see straight line growth? That's often a pretty aggressive forecast. What we might like to do is just kind of slow it down a little bit in the future and have a little bit of non-linearity in that forecast. And then we get a forecast that is still increasing, but maybe not increasing quite as fast. So and just to kind of hammer home the point as to why you might want to do this, go back and look at these previous trends, all right? 202 is kind of on the high side compared to what we observed. All right, so should I add 202 or should I average these together? Yeah, I kind of think 202 is like a good estimate based on like what I currently saw, but I might just want to tone it down for the future a little bit. And this would be a way to get something that looks a little bit more like these in here rather than this in here.